Hello everyone, and welcome back to our exploration of complex analysis, and today we're going to be continuing our journey through the realm of the complex plane and begin to start to build tools associated to the realm of calculus on the realm of C. So what do we know how to do so far? Well, we already know several properties of the set of complex numbers, and we know several new properties of functions whose domain is the set of complex numbers, whose range potentially could be all of the set of complex numbers, and several of the different things that these functions exhibit that they didn't have in the real plane. For example, exponential functions being periodic. We didn't have that before. We have natural log functions now that are multi-valued as a consequence of the periodicity of the exponential function. We also have that powers will rotate objects, not just scale them, which we didn't really have in the real world, right? So we have several new properties associated to functions in the complex plane, so we probably will anticipate that calculus behaves potentially slightly differently in the complex plane as well. So one of the safest places, at least in my opinion, to start building tools of calculus is that with the idea of sequences of complex numbers and the idea of what it means for a sequence of complex numbers to converge to another number. So obviously we're going to start with a sequence, zk, where k ranges from 1 to infinity, and it's said to be a sequence of complex numbers that converges. Now keep in mind, if you don't know what the definition of a sequence is, it's just a function that maps the natural numbers to some output. In this case, that's going to be equal to c. So we have k is equal to 1, 2, 3, 4, 5, 6, up to infinity, so that's the natural numbers to the complex plane C. So we're going to say that this sequence of complex numbers converges to some number L, which will be in the complex plane, if for all epsilon greater than 0, there exists a natural number n in the set of natural numbers such that for all little n bigger than or equal to capital N, we have that the distance between Zn and this point for which you claim it is getting close to is arbitrarily small, in particular less than the epsilon that was chosen for you. Right? So the sequence is going to be convergent if the sequence elements gets arbitrarily close to the number L eventually. When eventually? When n is bigger than or equal to this capital N, which is just a position in our particular sequence. So let's work through an actual example just sort of see how we would prove a particular value. So let's consider a complex sequence. Let's choose Zn to be equal to 1 over 1 plus I to the m. Right? So what do you think this sequence converges to? Obviously, as n gets big, the bottom is kind of like 1 plus 1, which is 2. So maybe this is going to exhibit patterns like 1 divided by 2 to the power of n, which will be equal to 0. So let's see if we can show that it is equal to 0 or not. If it is truly equal to 0, we should be able to make these sequences arbitrarily close, these sequence elements arbitrarily close to 0 for any given epsilon for us. All right, so let's see if we can prove it. If you want to pause the video and see if you can prove it on your own, that'd be cool too. All right, so let's let epsilon be greater than 0. Then, what would be the absolute value of this? So we have 1 over 1 plus I to the power of n minus 0. And obviously any number minus 0 is just equal to that number itself by properties of a field. So we have 1 over 1 plus I to the power of m. And then we can distribute magnitudes over quotients by properties of C. So we have 1 over 1 plus I, absolute value, to the power of m. And what is the norm of 1 plus I? Well, that's just going to be equal to the square root of 2. So this is going to be equal to 1 over the square root of 2 to the power of m. Which is going to be equal to what? So keep in mind, if little n is bigger than or equal to capital N, that means 1 over n will be less than or equal to capital N. So that means this expression will be less than or equal to 1 over the square root of 2 to the capital M. We just need to figure out what is that capital N going to be equal to. So we know that this needs to be less than epsilon. So what do we need to do? We can choose or let our capital N, and keep in mind this has to be a natural number, to be equal to the ceiling of the logarithm base square root of 2 of 1 divided by epsilon. And you're like, well, how'd you get that? In some sense, the trick is reverse engineer what you want. Right, so you want this to be less than epsilon or equal to epsilon in this particular case, and this is going to give you 1 over epsilon, or 1 over epsilon, which is going to be equal to epsilon in our case, which concludes the proof. So you pretty much solve this equation right here for what capital N is, and of course make sure that it is a natural number. Right? So we have that for any epsilon greater than 0, you should always be able to find a capital N such that all of your sequence elements will be close enough, quote unquote, and what is close enough? The epsilon that was chosen for you. In particular, they're close enough to this limit for which we claim it converges to, in this case, equal to 0. Now, you might notice one very apparent thing, that we pretty much turned our complex sequence into a real valued sequence, because what are we doing? Well, we're taking the norm of a sequence, which is going to produce a sequence of complex numbers. And this immediately gives us the first important theorem that you can use to prove sequences, and I'll leave this proof for you since it's actually not too tricky, but the limit as n goes to infinity of Zn will be equal to L if and only if the limit as n goes to infinity of the norm of Zn minus L converges to 0. It's very important to note that this is a complex limit, so this is in the realm of the complex plane, and this is just a real valued limit. A real valued limit. So if you know any tricks from the real analysis world, you can use all of those on this particular expression, but keep in mind, this is by definition the definition of a complex limit, provided that you can show that this is less than epsilon. And keep in mind, if epsilon is greater than 0, then obviously 0 will be less than whatever epsilon you choose. Right? So that's kind of a sketch of this proof of how you would justify that. Right? But keep in mind, pretty much what we're focusing on is that the norm is getting close to 0 between these two things. That's what we're actually showing when we say that a complex sequence converges to a number that is the norm between these two things is converging to 0. Now that we know how to consider limits of sequences of numbers, now let's switch to limits of functions, which in some sense can be viewed as a generalization of such things. So what are we doing now? So now we're going to take a function that's defined in the complex realm and define what it means for a function to converge to, at least in the liminal sense, equal to L, or 2L. So the limit of this function as z approaches z0 is said to be equal to L. If for any epsilon greater than 0, there's going to exist some delta greater than 0, such that if you make the domain elements get arbitrarily close to one another, and keep in mind, we're in the complex world now, so that means when I say z is close to z0, I mean like in a neighborhood of z0. So regardless of the direction for which you get close to this z0, the image elements of fz and L should be arbitrarily close as well. Right? So for example, L is located here, so you should be able to make your f elements as arbitrarily close as you want as well, provided that you make or have control over the domain element distance, in particular z minus z0. So let's actually take a look at a very basic example. So let's look at the limit as z approaches the number 2 minus I. Let's choose a basic function to start with, 5z plus 3. So we hope that all of the normal properties of limits still follow as they did in the realm of single variable, real variable calculus. That is, if you plug in 2 minus I into this expression, so I'll just throw a question mark here, is this going to be equal to 5 times 2 minus I plus 3, which will be equal to 10 plus 3, which is 13, minus 5i. So does this still hold? So this is going to be our conjecture value, and let's see if we can go ahead and prove it with the delta epsilon definition. And you might want to pause the video and see if you can do this on your own. So let epsilon be greater than 0, and let's also choose our delta to be equal to, I don't know exactly what I want to choose my delta to be, what will be, but we'll find out soon enough. So delta is going to be equal to something. We'll figure that out momentarily once we see how small we want to make it. So the distance between 5z plus 3, our function, and the value we think it gets close to should be able to be made as close as we want to each other if we have complete control over the domain distance. So once we simplify this, that's going to be equal to the absolute value of 5z minus 10 plus 5i. And notice that I have a 5 in common here, so that's going to be equal to 5 multiplied by the absolute value, because the absolute value of 5 will be 5. And then we're going to have z minus, and I want to focus on 2 minus I, so I'm going to focus out a minus 1 and write this as 2 minus I as well. Right, so this is going to be our domain distance that we focus on, which is going to be less than delta. So this is going to be equal to less than 5 times delta, and now we exactly know what we need to choose our delta to be, because we want this to be less than epsilon, so we can choose our delta to be equal to, or technically less than or equal to, epsilon over 5. So once we choose that, that's going to be less than or equal to 5 times epsilon over 5, and that's going to give us epsilon. So if we make our domain elements as close as we want as possible, then we will have as an outcome the distance between the range elements as close as we want. All right, so that we have that distance is less than epsilon, which completes the proof that the limit as z approaches 2 minus I of 5z plus 3 indeed is 13 minus 5i, which kind of baits the idea that the properties of limits will still hold in the realm of complex variables. Now let's do another example. For example, the limit as z approaches I of z squared. What do you think this is equal to? So question mark, maybe it's equal to I squared, which is equal to minus 1. So take a moment and pause this video and see if you can prove or disprove that this is indeed the limit of this particular function. So how do we start this proof? So as usual, we're going to choose an arbitrary epsilon that is positive, and we're going to be choosing our delta in a reverse engineer fashion to be equal to or less than or equal to some number, and that's going to be clear momentarily. So the absolute value of z squared minus 1, also known as z squared plus 1, this can be factored into using the sum of squares, z plus I and z minus I. Note immediately here that we have control over the distance between z and I, so this is going to be less than our delta. So this is going to be less than our delta times z plus I. Now, every time you have an expression that still has z in it, sometimes you need to force, unless you want to do something really clever, another z minus I in this particular expression. So how can we write I in terms of minus I? Well, that's just a 2i distance. So this is going to be equal to delta times z minus I plus 2i. Now, since we're working in a metric space under the absolute value, we know that this is a complex number, that's a complex number, so this will be less than or equal to delta times the sum of those absolute values, so z minus I plus the absolute value of 2i. The absolute value of 2i is just going to be equal to 2, so this is going to be equal to delta times, and we can make that less than or equal to delta and then plus 2. So it's going to be equal to delta times delta plus 2. So we want this to be equal or less than or equal to epsilon. So that's going to be equal to what? So now we're going to reverse engineer this. So if you want to solve this inequality for delta, you can do so. So what you'll realize from the quadratic formula that delta needs to be chosen to be less than or equal to negative 1 plus the square root of 1 plus epsilon. Keep in mind that epsilon is going to be a number that's positive, and a positive number plus 1 will always be positive. So that's going to be positive. In particular, it's going to be bigger than 1, and a number bigger than 1 plus minus 1 will be bigger than 0. So this delta will be indeed a real number that's larger than 0. So everything is safe in terms of the definition of our delta. So this is going to be less than or equal to delta, which is going to be negative 1 plus the square root of 1 plus epsilon, times 2 plus that thing, which is going to be 1 plus the square root of 1 plus epsilon. And you should find that that is indeed going to be equal to the square root of epsilon squared, which will be equal to epsilon, which completes our proof that the limit as z approaches I for z squared is indeed equal to -1. From the past couple examples, you probably already have some intuition that the properties of limits will still satisfy in the realm of complex numbers, and indeed, your intuition would be correct. In particular, the properties that will still work in the realm of complex numbers are as follows. So if we assume that the limit of f exists and is equal to LF, and the limit of g exists and that's equal to LG, then the linear combination of f and g, where alpha and beta are complex valued constants, the limit can distribute over that linear combination, and you'll just have alpha LF plus or minus beta LG. Right, so you can distribute over addition and subtraction, no problem. Also, it can distribute over multiplication, no problem. And it can distribute over quotients, no problem, provided that the bottom limit is not 0. And moreover, it can distribute into compositions of functions, no problem, as long as that composition at that limit exists. Right? Now, you might be thinking, well, what if I plug in z0 into fz over g of z and I get like 0 over 0, or infinity over infinity, or I infinity over I infinity, or something like that? Can I use L'Hopital's rule from single variable calculus? The answer is yes, but keep in mind, we don't know what derivatives are yet in the realm of complex numbers, or even how derivatives would even behave. But once we get there, don't worry, L'Hopital's rule will still be able to be applied in the realm of complex numbers for limits if you so desire to use it. Let's do a quick example of things that we actually can work with the tools that we currently have access to. Suppose somebody asks you, what is the limit as z approaches I of the expression z squared minus 3z, not 3i, but we could put the I there. Let's do 3z minus 5 all over z squared plus 5z plus 1. So by all the rules, provided that they do hold, and keep in mind the proofs of these will follow the same exact way as elementary real analysis in case you're curious and want to try that on your own. This is going to be equal to I squared, so that's going to be minus 1, minus 3i minus 5. All right, so that's not 0, so we're clear on that. And on the bottom, we're going to have minus 1 plus 5i plus 1, and that's not equal to 0, which is also great. So on the top, we're going to have minus 6 minus 3i all over 5i, and then we can simplify or write that in standard form as minus 3/5 plus 6/5 I as the limit of this rational function in the realm of C. Right? So limits can actually work in quite a nice way, but if you want a more rigorous approach, you can of course do the limit delta-epsilon definition if you so choose to. Now, let's define a very important thing or concept from calculus that derives from limits. So suppose that f is defined for all z in a neighborhood of some number z0, where epsilon is the radius of that neighborhood. Then we say f is continuous at z0 if there's a delta epsilon definition of this, but you get this definition almost as a corollary, so I'll just take it as the definition. The limit as z approaches z0 of f of z is equal to the function evaluated at z0. Right? So if the limit equals the function value, then we say it is continuous there. Right? Also, if the function is not defined at that point, but the limit exists, sometimes, again, we'll call that removable discontinuity. But we'll talk about discontinuities and their problems a little bit later on. But let's just mention a couple theorems that are almost immediate from the properties of limits. So if P maps C to C, with P of z defined to be equal to the sum from k is equal to 0 to n, and a natural number, of ak zk, where ak is a sequence of c, and n, again, a natural number. And most of the time we'll require that an not equal to 0 if you want to formally define the degree. So let's just, actually, why not? An not equal to 0. Then P is continuous on all of C. And why is that the case? Well, we can plug in any number to zk and add them up, multiply them, power them, and still get a complex number as long as everything is finite and defined, which it is with the realm of polynomials. So polynomials are everywhere continuous, just like they were in the realm of R. Now, if P and Q are polynomials, and we define R of z to be equal to the quotient of those polynomials, so that means R is a rational function, then R, this rational function, is continuous on all of C, take away this particular set S, where S is the set of all Z such that QZ is equal to 0. So as long as the bottom polynomial does not cross the, I guess you could say it, z-axis, or QZ does not generate the value 0, then it's going to be continuous at that particular point. Right, so rational functions, polynomial functions behave the same way they do in the realm of R. So is there any functions that we have in the realm of the complex planes that might exhibit potential weaker or stronger continuity than we had before? I'll give you an example, and I'll also give you a rigorous proof on how to prove that it is continuous on all the set of complex numbers. So let's get right into that. So the example that I want to work with is going to be the principal square root function. The principal square root function, which we talked about in detail in the last video. So this is the principal square root function. Because remember that radicals will be multi-valued, but this is just focusing on a single valued function, in particular the principal square root function. Now this is going to be continuous on all of C. Now in the realm of R, it was only defined on the positive real numbers and 0. But once we include the values in C, we have continuity on all of C, in particular at the origin. All right, so you might even want to pause this video and see if you can prove that this function is indeed continuous on all of the complex plane. So how are we going to go about this? All right, so let's assume or recall that the square root of z is defined to be equal to e to the 1/2 the natural log of z. And keep in mind that was equal to e to the 1/2 the principal value of the magnitude of z plus I arg z. So if you want to go in that particular world, that is perfectly fine, in particular the x plus iy form, but I will actually show you how you can prove, say, limits and continuity using the polar representation of our complex number, or our complex sequence rather. So again, our goal is to show that for all epsilon greater than 0, there exists a delta greater than 0, that if z minus z naught, non-zero, is less than delta, then f of z minus f of z naught will be less than epsilon for all z naught in C. So this is what we're trying to show. So not only is this true at that particular value, but it's true for every single z naught. So what we're going to do is we're going to show that this is true in polar coordinates. That means we should be able to make r as close as we want to r naught, and theta as close as we want to theta naught. Because keep in mind, our function can be represented in terms of its real and imaginary part, x and y, which should be as close as we want to x naught, y naught. And we can do the same for the polar coordinate forms, r and theta, with respect to r naught and theta naught, respectively. So let's see how this would work in the polar coordinate perspective. So that means the absolute value of z minus z naught in polar form, and you could do, and actually recommend you try this in Cartesian form as well, or rectangular form. That's going to be equal to the square root of r e I theta minus the square root of r naught e to the I theta naught. So what is this going to be equal to? So this is going to be equal to, by properties of the principal square root function, will be equal to the absolute value of the square root of r times e to the I theta over 2 minus the square root of r naught times e to the I theta naught over 2. And then we can add a mixed product term, and this is common for most limits, so we can induce a triangle inequality. Because we want our r and our r naught next to each other, and we want our theta and our theta naught next to each other. Currently they're separated, and we want to mix them together. So we're going to have the square root of r times e to the I theta over 2 minus, let's do the square root of r naught with I theta over 2, and then let's add it. So r naught e to the I theta over 2, and then we're going to have our square root of r naught e to the I theta naught over 2. And now we have two expressions, this one and this one. They're both complex numbers, so we can impose the triangle inequality on their sum. So what is that going to give us? So that's going to be less than or equal to, by triangle inequality, the absolute value of the square root of r e to the I theta over 2 minus the square root of r naught e to the I theta over 2 plus the absolute value of the square root of r0 e to the I theta over 2 minus the square root of r naught e to the I theta naught over 2. So what do we have in common with the first term? Well, we have a e to the I theta over 2 in common for the first term, and we have a square root of r naught in common with the second term. So let's just factor out those and see if anything happens magically with that. So this will be equal to the absolute value of e to the I theta over 2 times the absolute value of the square root of r minus the square root of r naught. And over here we're going to have the absolute value of the square root of r naught times the absolute value of e to the I theta over 2 minus e to the I theta naught over 2. Keep in mind, since we have e to the I something, in the norm of that, that's always going to be equal to 1. So we're going to have 1 times the absolute value of the square root of r minus the square root of r naught. And then the square root of r is going to produce a positive number anyway, so we can actually remove the absolute values on the square root of r naught. And we're going to have e to the I theta over 2 minus e to the I theta naught over 2. Now, I'm going to pull some inequalities that we learned in the realm of complex variables, in particular the square root of a minus the square root of b, and you can prove this using derivatives. This will be less than or equal to the square root of the difference between r and r naught. So that's the first thing that you should try and prove. And then for this next inequality, you can actually show that e to the I a minus e to the I b, where a and b are those theta and theta naught over 2's, will be less than or equal to theta over 2 minus theta naught over 2. And we'll actually give a proof of that because this involves some inequalities with I in it, but the proof's actually not too bad. So once we have this, well, what do we have? So now we're going to start choosing our distances, because what do we have here? Because we control the distance between r and r naught, and we control the distance between theta and theta naught. And now we have these two inequalities. So now we're going to have a delta 1 and a delta 2, right? So this is going to be less than or equal to, or actually strictly less than, or we can say less than or equal to, why not? So less than or equal to the square root of delta 1, and then the square root of r naught over 2 times delta 2. So what are we going to choose our deltas to be? You should keep in mind we're trying to force this to be less than epsilon for any given epsilon. So what we want to choose is let delta 1. So let's let delta 1, let's be a little bit more neater. So let's let delta 1 be equal to epsilon squared over 4. So let's do a half-half split. And then we're going to choose delta 2 to be equal to epsilon over the square root of r0. Now r0 can be equal to 0, so let's just add 1 in order to avoid that particular problem. And then we're going to choose delta to be equal to the minimum of delta 1 and delta 2. All right, so that therefore both of these things are switched on, and then we have that the absolute value of z minus z naught will be less than delta by design, right? Because if our magnitudes are arbitrarily close to each other and our arguments are arbitrarily close to each other, that means the arguments are going to be arbitrarily close to each other as well. So if we choose delta to be equal to the minimum of the two, then both are switched on, and then we can have our delta. So that means this is going to be equal to less than or equal to delta. So less than or equal to the square root of delta plus the square root of r naught over 2 times delta, and that's going to be less than or equal to epsilon over 2 by design and epsilon over 2 by design, which is going to be equal to epsilon. So therefore, we have that the distance between the image elements of square root of z and square root of z naught are arbitrarily close to each other, provided that z and z naught are arbitrarily close to each other, proving that the limit is equal to the function value at all points in its domain, and its domain is chosen to be z. So we have that the square root of z is continuous, for all z naught in C. Isn't that beautiful? All right, so that's how you do basic limits and continuity in the realm of complex variables. Obviously, we'll talk about differentiability in a lot of detail at another time, so hope to see you there. Take care.